Property 1, Certainty and Conditional Probability. Welcome back, everyone. Before we dive into today's new topic, let's take a moment to recap what we've learned so far. In our previous lessons, we established the foundation of conditional probability. We define the notation P of E given F to represent the probability of an event E occurring, under the specific condition that another event F has already taken place. Think of it this way. When we introduce this condition, we are essentially shrinking our world. We are no longer looking at the entire sample space, which we call S, as our playground. Instead, we are restricting our focus, narrowing our attention solely to the outcomes that are contained within event F. Building on this idea of a restricted focus, today we are going to explore a very specific area of this framework, the concept of certainty. We will be looking at two fundamental properties where the probability becomes absolute. Specifically, we will mathematically demonstrate the probability of the entire sample space occurring, given that an event has happened, and also the probability of an event occurring, given that the event itself has already occurred. By the end of this session, you'll see why these scenarios lead to a probability of exactly 1. Probability of the sample space given an event, P SF equals 1. To start, let's translate the notation into plain English. When we write P of S given F, we are essentially asking ourselves, if we already know for a fact that event F has happened, what is the probability that the outcome is part of our original sample space, S? If you're looking for an intuitive way to think about this, consider the nature of a sample space. By definition, the sample space S contains every single possible outcome of our experiment. Now, remember from our introduction that event F is just a specific collection of some of those outcomes. Because event F is a subset of S, any outcome that falls within F must, by necessity, also be inside S. So, if we are told that F has definitely occurred, there is no doubt left. It is a certainty, or a 100% probability, that the outcome is also part of the sample space S. Now, if you prefer a more rigorous approach, we can prove this using the formal definition of conditional probability. We know the formula for the probability of E given F is the probability of the intersection of E and F divided by the probability of F. Let's apply this to our specific case. In step 1, we replace the event E with our sample space S. This gives us the probability of the intersection of S and F, all divided by the probability of F. In step 2, we look at that intersection. Since the entire sample space S encompasses everything, the overlap, or the intersection, between the whole sample space and event F is simply event F itself. In step 3, we substitute this back into our fraction. We are left with the probability of F divided by the probability of F. Finally, in step 4, as long as the probability of F is not 0, any value divided by itself simplifies to exactly 1. Now that we've established that conditional probability essentially shrinks our focus from the whole sample space down to just the event that has already occurred, let's look at our first property of certainty. On this slide, we are exploring why the probability of the sample space, given event F, is equal to 1. This leads us perfectly into our next slide, where we will see a very similar logic applied to the probability of an event occurring given itself. Probability of an event given itself, PFF equals 1. When we write out the notation P of F given F, what we are essentially asking is, if we already know for a fact that event F has occurred, what is the probability that event F has occurred? If you think about this intuitively, the answer is quite obvious. It is a statement of absolute certainty. If the very condition we are given is that event F has already happened, then there is no doubt left. The probability that F happened is naturally 1 or 100%. But as mathematicians, we don't just rely on intuition. We want to see the formal proof. Let's use the formal definition of conditional probability that we used in the previous slide to prove this. First, we start with our standard formula for the probability of E given F, and we replace the event E with our event F. This gives us the probability of F intersection F, all divided by the probability of F. Next, we look at the numerator. which is the intersection of F and F in set theory, the intersection of any set with itself is simply the set itself. So, F intersection F is just F now. We substitute this back into our fraction. This leaves us with the probability of F divided by the probability of F finally. As long as the probability of F is not 0, any value divided by itself simplifies to 1. And there you have it. The probability of F given F equals 1. Now that we have established that the probability of the entire sample space occurring given an event is 1, let's look at our second property of certainty, which is found on slide 3. This property deals with the probability of an event occurring given itself. This leads us perfectly into our next slide, where we will apply both of these properties to a real-world example involving a 6-sided die. Real-world example. Imagine we are performing a simple experiment, rolling a single, fair, 6-sided die. First, let's define our boundaries. Our sample space, which we'll call capital S, consists of all possible outcomes, 1, 2, 3, 4, 5, and 6. Now, let's define a specific event, which we'll call event F. Let's say event F is the event that the number we roll is an even number. Looking at our sample space, that means event F contains the outcomes 2, 4, and 6. To apply the properties we just discussed, let's look at two different scenarios. In scenario A, we are calculating the probability of S given F. This is written as the probability of capital S. Given event F in this case, we are starting with the assumption that event F has already occurred, meaning we already know, for a fact, that the die landed on an even number. Given that we know the result is either 2, 4, or 6, what is the probability that the result is part of our original sample space, 1 through 6? Well, since every single even number is already included in our sample space, there is no way the outcome could be outside of S. It is a certainty. So the probability of S given F equals 1. Now let's look at scenario B, where we calculate the probability of F given F. This is the probability of event F. Given event F again, we start with the same condition. We know the result is even. Now, we are asking, what is the probability that the result is even? Since our condition and our target event are exactly the same, there is no uncertainty left. If we know it's even, then the probability that it's even is absolute. Therefore, the probability of F given F also equals 1. Now that we have seen the formal mathematical proofs for these properties, let's bring this down to earth with a real-world example to see how this looks in practice. As you can see, both scenarios lead us back to that same value of 1, reinforcing the idea of certainty we've been discussing. In the next slide, we will summarize these key takeaways. Key takeaways. First, let's talk about the concept of certainty. Throughout our discussion of these properties, you've noticed that whenever we arrive at a probability of 1, it signifies that the event is absolutely certain to occur, provided that our given condition is met. In the world of conditional probability, a result of 1 means there is no uncertainty left regarding the outcome. Next, let's revisit the sample space property. We proved that the probability of the sample space, given event F, equals 1. This is because the sample space, which we call S, is the big picture. It encompasses every single possible outcome. Since every outcome in event F is already contained within the larger sample space, S, if we know F has happened, it is guaranteed that the outcome is within S. Finally, we have the identity property. This is the idea that the probability of event F, given event F, equals 1. As we saw in our mathematical proofs and our dice example, if the condition itself is that event F has already occurred, then the probability of F happening is total. It is a certainty. All right, let's wrap up what we've learned today by looking at our key takeaways. Now, before we finish, I want to point out a very common pitfall that many students encounter, so please pay close attention to the next slide. Common mistakes. Now, before we wrap up today's lesson, I want to address a very common pitfall that I see many students fall into when working with conditional probability. It is the mistake of confusing P of S given F with P of F given S. It is easy to get lost in the notation, but remember, students often confuse the event we are measuring with the condition itself. That is, the event placed after the vertical bar. Let's look at the difference clearly. As we discussed in the earlier slides, P of S given F equals 1. This translates to, given that event F has already occurred, the probability that the outcome is within the sample space S is 1. This is always true because F is contained within S. However, look at the reverse. P of F given S. If we apply the formal definition, we get P of F intersection S divided by P of S, since the intersection of S and F is just F, and the probability of the entire sample space S is 1, the formula simplifies to just P of F. This means the probability of F occurring, given the entire sample space, is simply the standard original probability of F, and as we know, this value is not necessarily 1. It depends entirely on the event itself. To avoid this error, I want you to always remember this golden rule. The event following the vertical bar symbol is your new, reduced sample space. It is the foundation you are standing on. If you keep that in mind, you will always know which event is your condition and which is your target.